Mathematician Joseph Fourier once said, "Mathematics compares the most diverse phenomena and discovers the secret analogies that unite them." And if math had sounded that mysterious when I was in school, I might not have ended up a theater kid. Luckily, here at UCLA, Professor Terence Tao has spent his career helping us all understand how figures and formulas connect us to our universe and to each other. In his classroom, you'll see the beauty of a binomial, find the grace of geometry, and learn how to listen to the music of this universal language. In fact, his colleagues here call him the Mozart of math. And today we're here to talk about the future we're writing with these tools and the harmony or discord that they can create. So please help me welcome James and Carol Collins Chair and Professor of Mathematics, Terence Tao.
Thank you. Thank you so much for the opportunity to speak here. It's, in these times we need leadership. It's more important than ever. So, yeah, I'll be talking about, well, the whole world is changing, of course, but also mathematics as well. But we are a very traditional bunch. In many ways, the way we work today is not that different from the way we worked 100 years ago, 200 years ago. On the left here, we have a memoir by Augustus Cauchy, one of the great mathematicians of the 19th century. It's in French, and it's not typeset of a computer, but to a math graduate student here at UCLA, the textbooks that he or she would learn from are not that much different from this book, which was published exactly 200 years ago. We still use blackboard and chalk. In fact, we are very particular about what kind of chalk we use. We're maybe almost the last department that hangs on to them. And over on the right here, we have this coffee table book by Jessica Wynn. She's a photographer. She was fascinated by the math we leave on our blackboards, and she actually photographed, she viewed them as works of art, and she photographed them and made a nice little collection. Another way in which mathematicians are different, or at least have not caught up to other sciences, is that we still find it hard to collaborate. In the rest of our division, physics and chemistry, people have worked out how to collaborate with 50 people, 100 people, on Andrea's collaboration, for instance. But still in math, we struggle to work with, more than 5 people. And there are reasons. There's a high barrier to entry. I know you're not mathematicians, most of you. You may not have noticed, but a lot of math is rather technical, has a lot of jargon. And you need first high school math, algebra, and then calculus, and then graduate level math to even understand many of the problems we work on. So you already need a math PhD to even just begin working on many of these projects. Also, we have this very, very high standard of proof. If a proof has 20 steps and one of them is wrong, the whole proof falls apart. So if you collaborate with 20 people and one of them doesn't produce good work, you're in trouble. And our workflows don't scale. I told you we love our blackboards. We can have 3 or 5 people at a blackboard talking back and forth. It's amazing. We can't have 50 people at a blackboard. So we haven't figured out, until recently, we've not figured out how to collaborate the same way that the other sciences have done very successfully. So, are we missing out on all this good stuff? Well, things are changing. So thanks to new technologies and new culture, actually, new workflows are emerging. We are beginning to do genuinely large-scale projects. Still not quite as large as the other sciences, but we're going to catch up. If math was a social science, it would be as if, until recently, we could only do case studies. We could take an individual and interview them and do a fine analysis of one person. But now we can do population surveys. We can start studying thousands and thousands of problems at the same time. We're beginning to broaden participation. As I said, right now there's so much of a high barrier to entry. Mathematicians mostly talk to other mathematicians. But in other sciences, there are citizen science projects that involve the general public or academics from other disciplines, and we're beginning to have that here in mathematics. And we have this fancy new technology of AI and machine learning. We are still experimenting with how to use it properly. We know lots of ways how not to use it. But there are some positive use cases that are proof of concept. And the secret sauce that makes all this work is that there's a technology called formal verification. It was developed by computer scientists, but mathematicians have embraced it. It is specialized computer languages that you can feed in things like a mathematical proof. If you do it in the right language, it will give you a certificate that says this is correct, this is not correct, and it's not correct, where are the errors? And without this, none of the other developments would be possible. So I'll just briefly talk about one project that I started here at UCLA last year. It's called the Equational Theories Project. It is a project in algebra. Now, I don't want to talk about the specifics of algebra, but maybe in your high school algebra classes, you may have heard of the commutative law, x times y equals y times x. You may have heard of the associative law, x times y times z equals x times y times z, if you put the brackets the other way. And you can write many, many other laws like that. So what we did was we generated a population of about 4,000 or 5,000 laws. Now, in algebra, historically, algebraists study one law at a time. They do a case study. They take one algebraic law and they study all its consequences very, very thoroughly. But we wanted to do a population survey. We would take 4,000 odd laws and ask how do they interact with each other? Which laws imply which other ones? What is the landscape of algebra? And because of all the pairs that you could consider, this ended up being 22 million problems that we had to study. Given 22 million pairs of laws, which one is stronger than another? For example, does the commutative law imply the associative law? Now, a graduate student here at UCLA in mathematics, a typical problem, they could probably work it out in maybe an hour with pen and paper. But there's 22 million of these problems. And some of them are actually too tricky to do it in an hour. There are computers, and computers can handle a fair chunk of these problems at a time, but no computer program can sort of handle all of them. So there's no way that a single person or single program can do this. You have to collaborate. But then there's this other problem that if you have people coming in with 22 million proofs, and one of them is wrong, your whole project doesn't work. Someone has to grade 22 million proofs. So that is not feasible until recently. Okay. But nevertheless, we did this in 3 months with 50 people, some at UCLA, some international, most have not met. Professional mathematicians, computer scientists, people from industry, just members of the general public who like solving puzzles. We completed it in 3 months. We had to develop new workflows to do this. There's lots and lots of very diverse proofs that are coming in. Some were human-generated with pen and paper. Some were computer-generated by these things called automated theorem provers. Very, very early versions of AI, think of it like that. And then we had these chat rooms on the internet where we would try to collate them and figure out how to convert them to this proof-assistant language. It's called Lean, that verifies all these inputs. And then someone had to develop visualization tools to see what portion of our implication landscape was still missing and what needed to be done. And we had to direct, and that had to loop back to all the other collaborators. It was a really, really fun project to work on, actually. And we're hoping that this is a paradigm for future large-scale collaborations. Okay, so we'll talk about AI. This is the technology of the decade. So in principle, this is a really, really promising technology. And we're already using it somewhat. It's really great for secondary tasks. I can write computer code now to simulate all kinds of mathematics. It's so easy with these tools. It's great. And just recently, they've become useful tools for literature review, which also was a very tedious task in the past. If you feed them the right data sets, they can generate new mathematical conjectures. They can find mathematical patterns. We have a shortage of good data sets currently, but that's something that we're working on. But to me, the application of AI that's most exciting is that they are a universal translator. The really complicated topics in mathematics can be explained. You can ask an AI to explain at the level of a high school student, or you just tell it what you know, and it will try to match your language. And conversely, if an amateur mathematician wants to talk to a professional, if they use AI, in principle, they can speak with correct, using the correct mathematical jargon and in a really comprehensible way. And so I think we can really collaborate with other scientists, with members of the general public in ways that we've not been able to do before. But AI is a very flawed technology. It has many, many issues with it. The issue which concerns mathematicians the most is that it just makes mistakes, lots and lots of mistakes. The modern AI tools are not grounded in reality. They hallucinate all kinds of very plausible looking nonsense. And maybe in some other fields, this might be acceptable. Actually, it's problematic everywhere, really. But in math, it's particularly bad because of this 100% correctness requirement in our proofs. But we have these formal proof verifiers that are think of them as like extremely fussy graders. That they can take the output of a large language model and they can give it a correctness certificate, or they can point out the errors. And so they can filter out all the bad hallucinations and only keep the small percentage of actual correct statements. And it's only very recently we can experiment with this, but the proof of concepts are very promising that this could be a powerful combination and a way to safely use these AI tools. And I asked an AI to generate an image to illustrate this point. So the LM output is this sort of sewage-looking kind of mathematics, and then we have this filter to produce drinkable mathematics, I guess. Okay. So just to close, I've been here 29 years, not quite as long as Andrea, at UCLA, but I've always been very grateful of the opportunities here and the freedom that it's given me to explore new directions. This type of work is not what I was hired for to do here 29 years ago, but I very much align with UCLA's ideals, the idea that diverse communities can come together and talk and produce great things that they could not do on their own, and that's really informed my own research. So thank you very much.